August 28th, but you can watch it before. So the first thing that I want to cover is classification of second order linear partial differential equations, okay? And this will really break things up into categories that are really represented by the different canonical PDEs that we'll come across in this class that are physical manifestations of different systems, okay? So the idea is that if we have a second order PDE with constant coefficients, okay, and some inhomogeneity, we can write it like this, okay? And this will be our general form, and we'll label that star, okay? So here we have u is an unknown function of x and y that we want to solve for. Of course, y could be replaced with t in this case. And our right-hand side is not just some inhomogeneity, okay? But it could involve some nonlinear functions of u and ux and uy, okay? In particular, this can only involve the lower order derivatives, okay? So we can have nonlinearities, but we can't have them at the level of second order derivatives, okay? And remember, we could use t instead of y, okay? So that's our left-hand side. It's just some nonlinear function of all the lower order derivatives and x and y. The left-hand side is what we're going to call the principal part of our PDE, and it involves partial derivatives, okay, in x and y applied multiple times, okay? So this is really just writing the operator that's applied to the left-hand side. And we can immediately associate this with what's called the principal symbol, okay? Principal symbol, I'm just going to write as L hat of P, L hat P. And the idea is that this is going to be equal to something that maybe is going to look a little bit peculiar at first, okay? Complex exponentials, okay? You have x and y with those psi1 and psi2 elements as constants, okay? And the result of this operation is that we're going to differentiate with respect to x and y according to this operator. And by applying that to these complex exponentials, we're going to get something that looks sort of like a characteristic polynomial, okay? And this is just an alternative way of expressing the left-hand side of that second order PDE, okay? And it's really related to Fourier transform, okay, for wave number, if that's familiar to you, okay? We'll circle back to these topics when we cover chapter 7 of Shearer and Levy, okay? And really, this thing dagger, that's my dagger there, can be examined to classify our PDE stock, okay? So the key object, which may not be a surprise if we were going to compute one number from that polynomial, is going to be what's called the discriminant, okay? And you take the middle term squared and subtract 4 times AC, okay? This is just like what you get from the quadratic formulas, element inside the square root, okay? Or, in our case, we can just have d over 4, which we'll call delta, which is b squared minus AC. So for AC. Okay. B squared minus AC, okay? And so the second order PDE is called now one of 3 things, okay? It's going to be called hyperbolic in the case that delta is greater than 0 or b squared is greater than AC. It's going to be called parabolic if delta is equal to 0. In other words, b squared is equal to AC. We keep trying to write 4AC. And it's going to be called elliptic as long as you're in the other region, which would be delta less than 0, b squared less than AC, okay? So hyperbolic makes sense. It's the region that sits above this parabola, okay? B squared equals AC. B squared equals AC is along this parabola, B squared equals AC. An elliptic is going to be beneath it, okay? And some books use an alternate formulation, which would give you just a B, okay, in this spot here. And in that case, you're going to have delta equals b squared minus 4AC, okay? We'll use b squared minus AC here for simplicity, okay? The results would still be the same in either case, okay? So why should we care, okay? Why have this formulation? Well, first of all, it guides, okay, the appropriate initial and boundary conditions that we need for our PDEs. If we can characterize what kind of PDE we have. And also, smoothness of solutions is intimately related to the type of PDE that we're studying, okay? And it can also be related to what are called like the canonical PDE, okay, of that type, okay? So what I mean by that is, okay, for instance, the wave equation, okay, which we wrote down on the first day of class, UTT equals c squared uxx, okay? This is our wave equation, okay? This is the canonical, or sort of representative hyperbolic PDE, okay? Basically because, well, we can show UTT minus c squared uxx, that's like our formulation of this left-hand side here, okay? So replace uyy with utt, okay? And so if we just apply our theory from the last page, we have xi1 squared minus c squared psi2 squared is our principal symbol. So lambda is equal to 0, because b is 0, plus c squared. And this is equal to c squared, which is greater than 0. Okay? So any other hyperbolic PDE tends to behave like the wave equation, okay, with some caveats, okay? You get these sort of propagating outward solutions, okay? The other thing that's relevant to things like the wave equation are that you have dispersion relations that tells you how wave numbers travel along together. What's a wave number? Okay, well, it corresponds to the frequency of a periodic function that tends to propagate in sort of wave type equations. Okay, so the solution to the wave equation, or in lieu of any initial conditions, we're going to have a bunch of solutions. We're going to look like this, okay? E to the I psi x plus sigma t, okay? Where sigma is actually going to be some function of psi that's determined by the PDE itself, okay? So if we basically plug into the wave equation, okay, then what we get is that sigma of psi squared e to the I psi plus sigma t is equal to minus c squared psi squared e to the I psi x plus sigma t. Get sigma there, okay? And this implies that sigma of psi is equal to plus or minus I c psi, okay? And this really bears upon how these different wave functions travel along according to the wave equation, okay? So u of xt is equal to e to the I psi now, x plus ct. And we see something that's similar to what we saw in the transport equation, okay? We have these, not surprisingly, wave solutions, but the waves can travel forward or backwards, okay? And this is really typical of hyperbolic PDE, okay? You have forward and backward traveling wave type solutions, okay? And you often have a dispersion relation like this that tells you, depending on the frequency of your wave function, how is it going to travel through space, okay? And in fact, in this case, no matter what your wave number is, the wave function always travels in the same way. This is not true of other PDEs, and you'll see an example on your homework where that's not the case. Okay, so that's hyperbolic. What about parabolic type PDEs, okay? Well, as we saw in the last lecture, okay, backward parabolic PDE, okay, are not well posed, okay, usually, okay? So the heat equation is the canonical parabolic PDE, and if you try to run them backwards, you'll get nonsense, okay? So forward parabolic PDE, what do you know about them? Well, their solutions, if you think of the heat or diffusion equation, their solutions sort of spread out, okay? Diffuse, okay? And so our typical parabolic PDE is going to be our nice heat or diffusion equation. Okay, this is the canonical parabolic PDE, and UT in this case is, well, that's first order, right? So we actually don't have very many terms in our principal symbol, okay? So since the left-hand side looks like this, our principal symbol just ends up being minus k psi squared, psi 2 squared. So that implies when we plug this all in, we only have that c is non-zero. So our delta is going to be 0 plus 0 equals 0. So that means it's parabolic, as we said that it should be, okay? Now, the dispersion relation of parabolic PDEs tends to not be one that leads to traveling wave type solutions because of this spreading out, okay? So high frequency wave numbers tend to get mollified or smoothed out. And that's apparent in our dispersion relation, which we can work out, which is that sigma equals minus k psi squared. How do you see that? Well, if we plug this back in to our wave type solution, we get e to the I kx minus k psi t squared t. So basically, the higher order modes or the higher frequency wave functions or the really fast oscillating parts tend to decay much faster, okay? So we'll see this again when we come back to Fourier series solutions of heat and diffusion equations, okay? But the basic idea is that low order modes tend to dominate, okay? And physically, this should make sense. As time goes on, the higher order modes are going to smooth out, okay? And you're just left with the lower order modes. Okay. Last case of second order PDEs is elliptic, and these often describe equilibrium states, okay? Because you get elliptic PDEs from like diffusion operators without the time dependent part, okay? So we have usually nicely smooth solutions because they might be the steady state of like a two-dimensional diffusion equation. And of course, the canonical one is the Laplace equation, okay? And if we look up here at this, if this was a Laplacian on the right-hand side, this in 2D, this would be like the steady state solution of that, okay? So this is our canonical elliptic PDE, great. And we can work out all our results as we did in the other case. Uxx plus Uyy gives us this as our principal symbol, okay? So delta then is equal to 0 minus 1, or minus 1, which is less than 0, okay? And a dispersion relation is really less meaningful here, okay? Because we're usually not thinking about things that travel long in time, okay? And this is a type of equation that's usually solved on bounded domains, okay? And so in that case, the BCs determine our solution, okay? So you can read about generalizations to higher order in the first couple of chapters of Shearer and Levy. Okay. Another thing that you can read about in Shearer and Levy, okay, is general existence proofs, okay, for these types of PDEs, okay. But that really won't be a deep focus of the class, the kind of analysis that goes into what's called the Cauchy-Kova-Lev Skaya, okay, theorem for second order PDE solution existence, okay? The high points of that, okay, is that it really requires strong assumptions, okay? Most of the constitutive functions have to be C infinity, okay? They have to have a convergent power series, okay? And the basic result is really just that you get existence, okay, but not full well-posedness, okay? And oftentimes, you're not necessarily going to have a PDE where all of the components of the PDE are C infinity or have convergent power series associated with constituent functions, okay? And you usually need to assume something like C2 for uniqueness, okay? And so you can read that theorem, okay? But we're not going to